Okay, everyone, welcome back for week 9. So we're ready to go, pretty much. So Yisong, I think you said you're going first, so you're welcome to go ahead and share your screen. Okay, welcome back for week. Okay, let's see. So when you're ready, you can go ahead and connect. Okay, Yisong and everyone, are you ready to present? Hello, guys, can you hear me?
I can. I think Yisong is going to give a brief introduction first.
Yeah.
Do you, Yisong? Because I saw
can't
his
hear you.
mouse.
We can see your mouth moving, but we
Yeah.
can't hear you.
Yeah, he's still connecting, it seems.
Right.
Yeah.
Yeah, I know it's a little tough being in China and then trying to connect to Zoom on the outside.
Seems. Can you guys hear me?
Yeah, we can hear you now. Okay, Hengchang, I'm also going to declare you as a co-host, just in case my connection goes haywire.
Okay.
So I think you're granted co-host privileges at this point. Okay, Fiona, you message me. I will get back to you while we're in the middle of our consultation. Sorry, our lesson today. So I appreciate that. So while Yisong is getting ready, I think there was some problem with his connection. As I wrote on the general channel, we are going to continue 6101 for our reading group for next semester. And because we have two very prominent alumni from our group working on one, this course, and the other one is recommendation systems, we are probably going to do, 95% likely, to hold this reading group, especially on this topic. So we're getting a taste of it here as a preview over the next 2 weeks, just on conversational recommendation systems. Okay, so hopefully those of you who are interested in this and after doing your projects for 6101 for this semester, you want to rejoin for next semester, you're welcome to. So I think Yisong is back now, and hopefully his connection is a little better. So yeah, we'll let him go ahead when you're ready. So Yisong, you can go ahead and give the introduction when you're ready.
I think still there is some issue.
No, I don't think any one of us can hear you. Can anyone hear? No. Who is going after Yisong?
I think it's present sequentially.
Yeah, and me.
Okay, so maybe even though Yisong wants to give an introduction, his connection is just probably not strong enough to do that. So why don't we just go ahead with the second presenter first, and then come back to Yisong later.
Okay. So I'm first.
Yeah.
Okay.
Jiahao, are you okay?
Yeah, I'm okay.
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 So we'll let Yisong try to figure out his connection issues. And Yisong, feel free to interrupt whenever, just so that you can test out your connection.
Okay. Let me share my screen.
So thanks, Jiahao.
Hi, can you guys hear me now?
We can hear you. It's weak. Can everyone hear?
Yes.
Yes, I can hear him.
Okay, so Jiahao, then in that case, Yisong just came back in time. So
Oh,
you can have you can relax for a couple more minutes.
okay.
Okay, thank you.
Yeah, so seems that my my headphone is off. Yes, I'm using my internal speaker. Okay, so I'm going to share screen to my opening intro.
Okay, when you're ready.
Yeah. Can you guys hear my slides? See my slides here? Can you?
Yep.
Yeah. Okay, great. Yeah. So I'm very happy to give an opening for our reading group this week. Conversational recommendation. My master thesis is also on this topic. Let's go. Yeah. So first, a small example. What is conversational recommendation? I want to give an example of conversational recommendation on a restaurant booking platform. So now we have a customer, they want some sandwiches, and now the agent asks, which city are you in? The customer responds as Las Vegas. And then the agent asks two more questions, the nationality and also the rating. And finally, the agent becomes confident and recommends 10 items, with the user accept the fourth item. So this is a toy story about how conversational recommendation works. So let's talk about the motivation. Why we need such conversational system, a conversational recommendation system, meaning that we push traditional recommender system into conversational style. Why? Well, I believe the reason is information asymmetry. So talking about this, I think there are 3 points about information asymmetry. First point is that there's a gap between training data and testing data. Testing data here refers to that when the system is actually deployed online facing users with new requests. So there might be a gap between training data and testing data. It is better to converse with the user about their current information and preference. And the second point is the so-called cold start problem. It is often referred to a new user, a completely new user enter a platform. So the platform know nothing about the new user. So it's better to converse with the user. And the third is the user's preference may shift from time to time. So even if we have an old user, his preference may shift. So it's also better to explicitly ask his preference. So here is a bird view about conversational recommendation. It is an intersection of many existing research disciplines. So now I listed 4 major research disciplines. We have a traditional recommender system. Their key technologies include factorization machine, collaborative filtering, their neural variants. The second, it also relates to dialogue system. The key technology here includes is pipeline design, end-to-end neural models, reinforcement learning to find a better strategy, also the multi-round modeling, which is a bottleneck now. So many dialogue systems suffer from inconsistent and incoherent dialogue generations. And the third part is the human-computer interactions. We need a better interface. We also need to recognize users' intention. And the fourth discipline is user simulation. We need to build a fast user simulator to train model offline. The user simulator also needs to be have a broad coverage for multiple application scenario, and the user simulator is better to be unbiased. So we are going to talk about 5 papers today, and these papers can be categorized into 3 groups, 3 directions. The first direction is called question-driven approach. Today we have the work Q&R system in KDD 18, the Q in SIGIR 20. The key challenge here in this direction is that to ask better questions to identify user preference. And the second direction is called multi-turn conversational recommended strategy. The key challenge here is to find a better strategy to decide when to recommend and when to ask questions so as to minimize the turns of conversation, so as to increase the efficiency of the system. Third direction is on dialogue understanding and generation. The key challenge here is to understand user intents and preference through natural language. Today we are going to cover 2 pieces of the works. The first piece on ACL 20 emphasized on the dynamic nature of conversation, and the work on IJCAI 20 emphasized on the explainability issue. So let's welcome our speakers today. Yeah, I'm done.
Okay, thank you, Yisong. I am the first presenter.
I have stopped my share.
Okay.
Thanks, Yisong, for the intro.
Thank you.
Can you share? Can you watch it? Okay.
Yes, we can see your screen.
Okay, now let's begin. Hi, I'm Jiahao, and I will introduce the paper Q&R, a 2-stage approach toward interactive recommendation today. Sorry. Now the recommendation trend is make the system know more about the human, and we want to make a more accurate recommendation. So in the paper, this paper explores 2 stages of a single round of conversation with the user. The two stage about is first he will ask a user a question, and then the system will use the feedback of the user and to respond with a more accurate recommendation. The framework of this question and recommendation contain 2 parts. First is a question asking comment, just the question generation model, and another is an item recommendation model. In the paper, the item recommendation model is a video recommendation model. Before we introduce the flow of the framework, I want to introduce what is the one round of a conversation between the system and the user. First, the system needs to decide what to ask the user, and then the user will give a feedback. After that, the system needs to decide how to adapt the response and change its model according to the user provided feedback. Just like the picture, when a user comes and the trigger will make a select. If the result is no, and the user will go directly to the item recommendation model. It is traditional, and the video recommendation model will give a response to the user. And if the result is yes, and the user will go this flow, and we will use our question generation model to generate a relative question. For example, here, would you like to watch a video about a specific topic? And then we will capture the user's feedback. with the user feedback, we will use the item recommendation and some other information of the user to give a more accurate recommendation. Last, the framework will collect the user feedback and to enhance the user profile so that we can make a more accurate recommendation next time. The paper question generation model and item recommendation model is based on two tasks. Yeah. These tasks are about two questions, and the question's core area is the topic. In the paper, they want to use the topic to make the recommendation more useful. For example, why they want to use topic, not other information, because we know use the topic, they can capture user interest, and when asking questions, we can cover a large interest space. For example, if we use the topic, we may include some information, for example, the state of the user and the character of the user. Then now let's discuss the two tasks for this model. The first is, what is the topic of the next video a user would want to watch? This means that how can we determine the question of the topic of the question? For example, how can we predict the topic ID associated with the next video to be watched? And the second question is given the most relevant topic of the to be watched video, what video will the user be most interested in? It means that we now have some information. For example, the user watch history and other information. For example, the feedback of the user and how can we use this information to predict watch the video at next time. Based on these two tasks, then we discuss the model about the question ranking model. Because the watch history is sequenced, so the paper choose to use Jiahao to capture the relationship between the screens as a network architecture. The input is the watch event of the user. For example, the network will use the watch history of the user, and the output is a conditional probability distribution of the topic a user will interested at the next time. And the objective is to maximize the log probability of the observed events, and the function is here. Now let's look at the picture again. When a user come here, and we will use the watch history of the user to input the question generating model, and we will generate a relative question for the user. And this is the question ranking model. And another model is a video response model. Because we generate a relative question to the user, and we will obtain the feedback of the user, and now we have more information than the question model. For example, we now have the watch history and the feedback of the user. So how can we predict the next video more accurate? The paper proposed two methods. First is restricted output. The network architecture of this model is the same as the topic RNN. We only limited the output. For example, we only limited the video topic queue. When we use this method, the output will only in the topic queue. And another method is post fusion. Because we want to use the label topic ID we know from the user feedback. So we want to merge the information in the network in order to make a great effect. In order to make a great effect of the feedback. So the paper to use post fusion, and he will connect the topic ID with the GRU output, and then use this connect to pass to the ILU, and output the recommendation videos. Also, the training objective is to also like the question ranking model. It wants to maximize the log probability of the observed event, and give the repetitive part watch and the repetitive topics. These two models are the main components of this framework. And now let's talk about some experiments. In the paper, we performed 3 sets of the experiments. First is on a data set of YouTube user screens, and we compare different models for the separate tasks of question ranking and video response. In the second, we explore the relative improvements in video recommendation, and that we test on the user onboarding UI. Just like the picture, picture talk about the question ranking result and the video response result. From the picture, we can see that our method topic RNN have the result is very good than other models. First is random and popular and multi-class BOW. From the picture, we can know that it's important to capture the watch history screens of the user. And from the picture, we can see with the feedback of the user, we can have better recommendation. And the restricted output and post fusion are the methods we talked just now. And the post fusion restricted is used restricted on post fusion. From the data, we can see that there is no need to use restricted on the post fusion. And we also make a test on YouTube homepage, and the baseline is a production baseline. It is a highly optimized baseline, including also use RNN network. And from the result, we can see that our method have a 0.07% improvement in time spent watching video, and our method also have a 1.23% improvement in terms of the number of users who open the recommendation video. From the result, we can see it seems that the improvement is very small. But if we use the method in a large scale system, for example, YouTube, the improvement is very large. And we also test the ranking component in the context of creating a more enjoyable experience for casual user. From the red picture, we can see with our method, the watch time of user improve about 4%, and more users want to complete the onboarding UI. And when we generate a specific question for the user, and the user like to select specific topics of them to give them more accurate recommendation. Okay, the paper is just like I talked just now, and now let's make a conclusion. Q&I is the first work on learned interactive recommendation. And his main idea is very simple. It is used to split the video recommendation to two parts, and the first is a question generation model, and the second is a video recommendation model use the feedback of the user. Yeah. Also, about this paper, I have some question about it. Just like we talked, when a user when a user come, it will use the trigger to decide which flow he will go through. And the paper not introduce the trigger. It only says that the trigger is very important and it can make very important. It can have a great influence on the model. So I think I think it is important to talk about the trigger because the trigger is very important. Anyone know?
Okay, so Jiahao asked a question, right? What do you guys think about this idea of a trigger to decide whether to ask or decide to recommend? So I think later we'll get to Yisong's paper, which he authored with Hengchang and myself, but he's the primary author on that. So of course he can say a lot of things about how he studied that issue. But maybe the rest of you can give some opinions about what you think.
Okay.
Anyone want to volunteer a suggestion? I mean, this is sort of like the idea about taking initiative, right? Whether the system is going to take the initiative to be recommending, or whether it's going to take the initiative to ask a clarification question. So what could be some factors? You can say here out loud, or you could say in chat, either one, about what factors you might want to use to decide to make this decision.
Sorry, I think that it really matters a lot whether the entire system has enough confidence in recommending a reasonable result. So basically, if the system has a certain level of confidence, then it's likely to make a recommendation. If it's not reaching that confidence level, I think it should ask to improve its model.
Okay, so Shinza has, I think, a very good basic idea, which is to say, I look at the confidence on potential recommendations, right? If I have good potential recommendations, then maybe I don't mind giving the suggestions, right? Are there any other criteria that we could consider? There are actually lots. So I'm wondering, if you can think of it, not necessarily just from a mathematical perspective, but certainly, yeah, confidence is one thing that we would use.
I think maybe it's related to the idea of exploration and exploitation. So maybe the system at a certain point maybe want to ask for just to explore what are the interests, but sometimes it also, in order to provide accurate recommendation, it just exploits what is already known. So it's this kind of trade-off.
Mm-hmm. So the exploitation trade-off is a very general one, and we can frame a lot of problems in that way. So I think that's a very good suggestion, that we can use this idea of in reinforcement learning, right, where we decide whether we want to pursue optimal policy that we already know is pretty good, or whether we think the optimal policy is somehow not informed enough by evidence, and we want to go ask. Okay. Okay, Jiahao, you also asked about another question, right? So you put another question here, like baseline. So what do you mean by that? Can you clarify?
Yeah, because I think that the paper did not introduce the baseline. He only said that the baseline is very good, but our model is better than it. So I think it's important to introduce the baseline details in the paper.
Yeah, so in general, when we see papers like this that don't tell us the baseline, this can be a warning sign, either that, the area is so new that there's no suitable baseline, or, the paper is not as credible, they don't bother telling us enough about their experiments. They just want to tell you how good their work is, right? So we always have to read with a grain of salt. Of course, there's a lot of problems in writing a paper anyways, right? You usually run out of space. So you need to think about how you present things that are well-grounded. You know, if they don't give you a baseline and they don't analyze their models enough, this is a good reason to, you know, discount a little bit the credibility of the research until you're able to replicate it. Yeah, so that's a good point, right? Can we think of good baselines that we might use here? Right, so if we have a triggering system, you know, a trigger might be always recommend everything, right? So you could ignore the trigger aspect and just always recommend, okay? In the recommendation algorithm, you can use a content-based recommendation system that doesn't really have much of a model of the user's dialogue, right? Those would be ideal cases where you're treating, you know, the dialogue is not as a useful novel aspect in incorporating in the recommendation system, which standard recommendation systems don't, right? So those are simple ways. I think the premise and the idea of this paper is fairly simple. So I think it's a useful paper to look at to ground our basic understanding of. Okay, other questions from other people? Hengchang, any question from you? Your microphone is not on mute, so I'm wondering whether you have a question.
No, it's
Okay.
very clear.
No. Okay, good. All right, let's thank Jiahao, and let's move on to our next presentation. So this is a good baseline to start with. If it doesn't have a baseline, then we can use it as a baseline for the rest of the papers. Okay.
So I think I can be the next because I also doing the same topic that is question-driven approach. So it's kind of the next step of the Q&R.
Okay, let's go for that then. So Hengchang, you're next.
Okay, so following by the Jiahao's presentation, I also introduce another work that is kind of the question-driven approach conversational recommendation. Okay, introduce first. So as its name shows, this kind of CRS is kind of the introduce the question from the agent and give and receive the feedback from the user to update the strategy of recommendation. So it can be one or more rounds as Yisong introduce. So usually it asks questions about the attributes or topic or categories of items to narrow down the recommendation range. So another work here, I introduced the paper published in SIGIR this year named question-based recommender. It asked the simple question, including the entities related to target items to adaptive update the user latent factor and item latent factor. Actually, this is a very interesting and work that can bring some vision to the CRS workers. Actually, the author proposed that this is the first work that incorporate online MF and question asking for item-related features. Actually, this is also indeed the first work that I have read in this direction. So, for example, for the problem, for example, with determined number of questions, the agent expect to locate item of interest to user as quickly as possible. In this case, actually in this paper, the author defined the round of conversation previously, for example, the 5 round or 10 round or so. For example, in this case, from the first round, the agent can narrow down the user interest to cotton-related items, and also based on the historical interest interaction data. For example, the user tend to have interest with some certain kind of cotton towel. This is his potential preference ranking list, but the agent is quite unsure with some kind of for example, the beach tower and the bathroom tower in the second round and the third round. So based on this kind of unsure, so and based on the generalized binary search idea, the agent asked two questions to update the user's preference distribution and finally give top ranking items in prediction. So this is the framework of the QREC. It contains 5 modules. The first is training the parameter of recommendation system on existing historical interaction data first. And another is to update the recommendation system parameter round by round in the conversation. Actually, this is the most novelty in this work. And finally, is to adjust its recommendation strategy and give the final recommendation. Also, so it can be divided generally into this corresponding 3 parts. The first is latent factor building in recommendation. And the second is the question generation. And the third is the final recommender output. Actually, I think the most conversational recommendations the task can be divided into 2 parts. One is the more focus on the recommendation, how to make a better recommendation. Another is to focus on the question generation or the dialogue generation. So actually this work is mainly focused on the previous one, the recommendation, how to adjust its strategy round by round in the conversation. In this paper, it used the MF as its base, the matrix factorization. The general idea is to minimize the loss between the prediction and the truth data. When the prediction is calculated by the dot production between the vector of user latent factor and the item latent factor. Based on this idea, this paper used a variant of MF called the probabilistic matrix factorization as their online and offline training model. The difference is the latent factor and noise between the rating and prediction all have some kind of constraint, that is Gaussian distribution. So they all follow a kind of Gaussian probability distribution separately. So thus the problem definition in this paper can be shown as in the screen. So the user latent factor, item latent factor are following the Gaussian distribution with the mean is 0 and the variance lambda is which is a hyperparameter modeling the variance in the latent factor. And there are 2 metrics storing the interaction data. The R is the historical interaction and the Y is the online feedback from the conversation. They are all following the Gaussian distribution with the mean is the outcoming from the latent factor. The P and the Q here is also the one of the novelty. The author proposed that he also proved that using the P and the Q into the PMF can help the model fit in the truth data better. The loss function can be divided into 2 parts. The first is the rating matrix error. Another is the online affinity matrix error. The gamma is the trade-off between these 2 optimization. Initially, the Y is a 0 matrix because there are no feedback in the conversation, so they're all 0. It can be updated sequentially by the question-answer pair. For example, from the feedback, the user say he loved cotton and tower. This is 2 separate attributes, but a certain kind of item only has 1 attribute, then it will be allocated with 1. If it contains 2, the score of Y will be 2. Okay. So Then for the question generation, actually this part is quite simple. The first is the because the question asking is a template based, and the question learning is try to find the suitable entity. So just fill it into the template, then can generate the question. So how to find the suitable entity? Here are the steps. In different round of conversation, we can have different feedback factors. That is Y, and the I here present the round of the L. Sorry, the L here present the round of conversation. The first round, second round, third round. The user preference can be directly related to the Darklet distribution with parameter alpha to adjust the extent of concentration. The alpha has initial belief calculated from the offline matrix. So this the pi is the finally user preference distribution. Because this work only generates the template-based question. So basically, it's just need to define the correct entities, which may narrow down the scope in most extent. The first round is presenting whether the entities is in the document of M items. If it is in the document, then record 1, else record -1. The second row shows the user preference distribution calculated by the affinity matrix. The goal is to find the entity E leading the sum of production of between existence and the preference closest to 0. Actually, this is the general idea of binary search. For example, just give an example. For example, for the tower A, some documents, some kind of document do not have the entity tower A, but the preference of user only focus on this this document. So we can say that the system is kind of sure that the user do not like tower A, this kind of attributes. On the other situation, if they fit well, it can be indication that the user liked tower A. So the goal is to distinguish the less obvious judgments, making the user preference distribution even more polarized. So the system just want to ask the question about that the items they are unsure. Okay, so the question asking is quite simple, just to fill the entity into some kind of template, because this is a very simple question and answer. The answer can just be 3 options: the yes, no, or unsure. So the question can just be the do you like something? Okay, the experiment, this paper used 2 kind of data, the off from the Amazon. So actually they give the very similar results. So here I just show the first data set result in this presentation. So the evaluation, they also use 2 kind of data. The first is the simulating user. That is in a kind of interaction matrix, it removes some part of interaction and okay, I'll create another slide. For example, the user liked the Cotton Hotel Spa bathroom tower. Okay, then it will automatically generate a kind of conversation based on this preference. So like to specify some attributes in the item. Okay, so firstly, the experiment, the results compare different performance in this paper. By the different evaluation metric, the average precision, the mean, the MR, the mean, what's rank? I do not quite remember, and the NDCG score. Firstly, we can see that the QMF is better than the PMF. So this is the one conclusion that the user make. The adding P and Q can improve the model capability of filtering. And also secondly, the neural MF is better than the PMF. This is the neural MF apparently can capture more nonlinear relationship than the others. And finally, the QREC in the interaction base compared with other interaction baseline, where the QMF plus random is can represent the random question selection. So compare with that, the QREC's binary research is apparently better. So, and for the co-star problem, is also the one of focus the other concern. That is, he think by using the dialogue, from the dialogue, the user preference can be more clear, rather than just using one single interaction data. So for the co-star problem, because the co-star problem is that the user item interaction in which user or items never appears in the training set. So actually the PMF does not really work for co-star user and co-star item, but the QREC model can still achieve high recall, average precision, NDCG, and the MRR score. For the offline initialization, the conclusion that is the offline learned parameter from historical rating can indeed capture some general trend and provide a generic to guide the model. The finally is the user study, because the user study also draws some conclusion. The first is the average user, in average, user tend to answer about 15 questions. So, and the second is the answer are not totally correct. And the third is the QREC is relatively satisfying, that is easy to answer, which is also important metrics for the conversational recommendation system. And third is, okay, it's kind of agree with the previous result of simulating user. It's still achieve good results, even in the user study. Okay, so by conclusion, this work is the most novelty is incorporating the offline MF training and the online MF training. I think it's very useful for lots of others' work. Okay, my part is finished. So do you have any question?
Okay, let's thank Hengchang for his presentation. Okay, so we are up again against another fairly basic paper for this that looks at more traditional ways, not using neural networks, but using probabilistic analysis, Bayesian analysis for how to do the recommendation process. So does anyone want to try to summarize what Hengchang presented and contrast that with what we saw in the earlier paper presented by Jiahao? Just go give it a shot. Again, this is more a reading group, so it's not a presentation or lecture group. So it's good if we all try to converge and understand.
I think as Hengchang emphasized at the conclusion, so the main difference to me is like one is like using offline training and then test it online, while the QREC presented by Hengchang also has this online training part. Yeah, but both of them, they are using, like the first page of the Hengchang's presentation slides also show the same kind of model as what Jiahao represented. Yeah, both using it both involve the like question, then they were both need to decide whether to ask a question and then formulate think about what to ask and then generate a question and then do the recommendation. Yeah.
Yeah, true. Actually, I think the main difference between this work and the work Jiahao presented is actually in the Q&A is kind of the incorporated the user feedback directly into some kind of sequential generation, a prediction model. And in this work, it's actually can, because the MF is kind of the transparency algorithm. So actually it can directly update the user latent vector and the item latent vector online. So it's very interesting in this point.
Okay, so one we would say is a more direct model, the earlier one that Jiahao presented as well. And then for this one, you have a factorization approach. So it's directly updating all of the distributional properties, the multinomial distribution on the items.
Yeah, true. Actually, yeah, true. Actually, this can also bring some vision for the neural method. Actually, is the main idea is to updating the user belief, the preference belief among the items.
Mm-hmm. Okay, so I'd like you guys all to think about your own work in using a recommendation system. And you can think of a recommendation system as not very different from a search engine. I mean, the search engine is giving you recommendations for documents, right? In some ways, it is a recommendation system. So if you've taken search engine technology before, how is a search engine differing from a recommendation system? What's a key difference that we're missing from search engines that are not usually factored in? I mean, now they're factored in, of course, but in the typical lectures that people give about search engines, what components are we not really including that we are when we talk about recommendation systems?
Like user historical data is not considered when we are searching, but in recommending, that is one of the key components, what I feel.
Yeah, so Sunil is exactly right. When we think about a search engine, we're optimizing relevancy against the query. Right? We don't really care so much about multi-turn user preference or user modeling, right? And what a recommendation system said is, that's not good enough because I'm making a recommendation. This is a personalized recommendation. So of course, personalizing means I have to have a user model, right? And I have to know more about the user and their context. So we're seeing fairly, at this point, fairly primitive systems for deciding what a user likes, right, in terms of distributional qualities, but not modeling any other latent variables about, for example, information need, which is, again, a search engine concept, right? When we use a search engine, the literature basically says you have an immediate search query, but that search query is sort of an observable variable to a hidden latent need, right? So you have a latent need to, I don't know, restock your pantry, or to you study for an exam, or to, research a library, or to do a project, okay? And then you express these queries out with an intention, which becomes an observed query, right? So right now in recommendation systems, the query is sort of very primitive, right? Because we are not really giving any queries. A recommendation system is obviously to help people not need to formulate a query, right? It's sort of like a browsing system. I present items to you and you just prefer, right? So the onus becomes more on the engine to provide items and to justify why, because the justification is basically sort of like the hidden intent of the user. If you'd like junk food day on Fridays, for example, then I have to recommend that particular fried chicken restaurant or that pizza delivery service to fulfill that need and to tell you this is why I think you might want it on Fridays. Okay, so that's a shift between the control, the axis of control, locus of control of information gathering, right? And I'd like you to think about that a little bit more in terms of then what is a result of this, right? Like if we take it to a more of extreme process, what can we say? Do we end up with an agent that bosses you around, right? That henpecks you and says you should be eating your vegetables and you should get on sleep on time, all these things, or whether you want to take more control back as a user. You don't tell me what to do. I'm going to eat what I want. I'm going to go sleep when I want, etc. Okay, and how do you find the right balance between these two things? Okay, up to now we haven't seen much on how do we decide what item or how do we express what item is interesting, right? So we're sort of like not dealing with the natural language part. It's just more like a math of recommendation and preference and distributional properties, right? Trying to figure out the latent variables of that. So maybe we'll see a little bit more of that later on. Okay, so these are just things for you to think about. I think, again, maybe if you guys have questions or concerns, maybe we can try to discuss for a little while before going to the next paper. Anything that you guys want to talk about? I'll give you a full minute to go think about it, because I think it's sort of more interesting to have a little bit of discussion. Okay, nobody's game right now, so I guess we'll come back. I didn't wait the whole minute, right? I think I waited maybe about 15 seconds at most. Okay. All right. I'd like you guys to think about what the context of where the balance is shifting. Like I've told many people in my group, one of the big things that you need to do in scientific research is think strategically about research, not just gut reaction about what you can do given the current state of the art. So having a little bit of strategic vision about, okay, where is this going? We had search engines in the 90s and thousands, and now in the 2010s and 2020, recommendation systems are not being just a relegated corner of a console, but becoming the more prominent thing, right? Nowadays, you can still search the App Store, but you go to the App Store and you're faced with recommendations right there, right? It won't be long before, Google does this type of thing already. They used to have a very clean homepage, but now even Chrome already suggests or recommends things that you do based on your past activities. So that is going to become more ubiquitous, right? And where is the logical ending for all of this, right? As we go into more complicated structures between users and computers, right? And I think you can also relate that a little bit to what we have been talking about in the last couple of weeks. We've seen in natural language generation, the blurring about what users write and what the computer writes. Nowadays we're quite used to auto-completion, right? Emails where whole words are being inserted. Sooner or later, it'll be whole sentences or whole paragraphs being inserted by the computer, and you will have some control over that, but maybe you won't be very careful about how the machine says it. Okay, so what does that mean about recommendation systems too? Okay, because there's a logical conclusion to that I'd like you to think about. Just play it out. If you like to read sci-fi, a lot of us do as computer scientists, and you can imagine the Black Mirror episode or whatever you'd like to watch that tells you about what has gone wrong with natural language processing and recommendation systems. Okay, so your lecture just wasted another 5 minutes of your time, so I will go on to the next presentation.
Oh, should I go after Hengchang?
I think we can follow the Yisong's introduction in the separate three part.
Okay.
I do not quite remember who.
I think it's Jiaqi's turn. Yeah. Hi, Jiaqi.
So Jiaqi, yeah, you can go ahead and share your screen and go ahead. Okay.
Can you see my screen?
Yeah.
Okay, so I'm going to talk about the paper estimation, action, and reflection. And it's the paper that Pop-Min just mentioned about the multi-round scenario. We know that in the real world, the concession recommendation is usually in a multi-round scenario where the system interacts with the user by asking a question or recommending items multiple times until the task is successful or the user leaves the concession. And the core issue here is exactly the question that Jiahao asked. When should we ask a question and when should we recommend items? We know that if the system doesn't get enough information and it recommends some items to the user, then they might be rejected. And if we ask too many questions, the user will be impatient. So the question here is that how can we make a balance? For a multi-round conversation recommender system, there are three fundamental problems that need to be solved. So the first question is that what attribute to ask? So each time if CRS need to ask some questions, it need to choose what attribute to ask. For example, the system may ask, do you like this attribute or not? And the user will answer yes or no. And the problem is that how can we find the user's preferred item in fewer rounds? To achieve this, the conversation component need to consider whether the user will like the asked attribute. And if we ask this question, will the conversation be shorter? And the second question is when to recommend items. So when the system gets enough gets enough information, it need to recommend items to the users. And the question is that how can we know the proper time to push recommendations? In intuition, we know that if the candidate space is small enough, which means that if there are only several items in the candidate list, we can recommend them to the user. And if asking additional questions is already not useful or helpful, or maybe if the recommender is confident enough that the user will accept the recommendation, it's also a good time for the conversational component to make recommendations. And the third question is that how to adapt to users' online feedback. Each time the CRS asks a question or make a recommendation, the user will give some feedbacks, such as yes or no to a queried attribute, or accept or reject to the recommended items. And the problem is that how can we adapt the system when the user gives a positive or negative feedback to our actions? CRS usually includes two components. One is the conversational component and the other is the recommender component. And in this paper, the authors proposed a new conversational recommendation framework named estimation, action, reflection. and it consists of 3 stages: estimation, action, and reflection. The estimation stage builds predictive models to estimate users' preference on both items and attributes. And in the action stage, the system learns a dialogue policy to determine whether to ask attributes or recommend items based on the estimation stage and the conversational history. And the third stage is reflection, which updates the recommender model when a user rejects the recommendations. Next, I'll introduce them one by one. So the first is estimation. The purpose of the estimation stage is to estimate the user's preference on both items and attributes. They use the factorization machine as the predictive model. Given user U and his preferred attribute in the conversation, PU, and the target item B, we can predict how likely the user U will like the item V by this function. Here, U is the embedding of the user, and V is the embedding of the item V. The first term, U transpose V, is the general interest of the user on the targeted item, and it's a common term in the factorization machine model. And the second term considers the relationship between the target item and the user's preferred attributes. So to train the factorization machine, they use a pairwise Bayesian personalized ranking objective. The loss function of the traditional BPR is like this equation. Here D1 is a set of tuples U, V, V prime, and V prime is V prime is non-interactive item, and V is interacted items. And here the sigma is sigmoid function. Here the traditional loss function assumes that the interacted items should get higher scores than the non-interacted items. However, in the multi-round scenario, we need to consider the items that contain the user preferred attributes better. For example, if a user likes a Mexican restaurant, we need to rank his preferred restaurants among all the Mexican restaurants, but not other restaurants, right? So to deal with this, we can use 2 types of negative examples. One is the non-interactive items, as in the traditional BPR loss function, and the other is non-interacted items in the candidate set. And the new loss function for the items is like this equation. The first loss learns the user's general preference, and the second one learns the user's specific preference given the current candidates. I just introduced the loss function to predict the items and to find which item to ask in the which attribute to ask in the conversation. We also need to predict the user's preference on the attributes. We can estimate a user use preference on the attribute P by this function G hat. Here U is the embedding of the user and P is the embedding of the attribute P. And PU is the set of U's current preferred attributes. And we can also define the BPR loss function for the attributes. Here we assume the attributes of the ground truth item V should be ranked higher than the others. And to predict the preference of both the items and attributes, the total loss total loss is set as the sum of the two loss functions. Well, when we are training the model, we can first optimize the first term, and after it converges, we continue to optimizing the second loss. We can do this iteratively, and it will converge in several iterations in practice. The second stage is action. So after the estimation stage, the action stage need to find the best strategy for the question when to recommend. To solve this problem, the author use a reinforcement learning model, and the purpose is to make a successful recommendation in a small number of terms. Here, we focus on the strategy, and we don't care about the method to generate questions and understand the dialogue. The state vector for the reinforcement learning model consists of 4 components, which uses the information of the recommender component and the dialogue history. The first state vector is as entropy, which encodes the entropy information of each attribute among the attributes of the current candidate items, and it's of size. It's the same size as the number of attributes, and the i's position denotes the entropy of the attribute pi, and the intuition here is that asking attributes which asking attributes with large entropies helps us to reduce the candidate space and benefit finding the desired items in fewer terms. And the second state vector is as preference. The user's preference, which encodes the user's preference on each attribute. It's also of size as the number of attributes, and the ith dimension is estimated by the G hat function for the user's preference on the attribute. The intuition here is that the attribute with high predicted preference is likely to get positive feedback. And the third state vector encodes the conversation history. At each dimension t, we will put number -1, 0, or 1, and -1 represents a recommendation is failed, and 0 represents asking an attribute that is not preferred. 1 is represents asking a preferred attribute, and this state vector is useful to determine when to recommend items. And the last state vector is as length. It's the binary representation of the length of the candidate list. And the intuition is that if the candidate space is small enough, we can push a recommendation and avoid unnecessary terms. The action of the conversational component is chosen by a policy network, Pi. It contains two fully connected layers and maps the state vector S into the action space A, and the action space includes all attributes and a single action for recommendation. And the output will be a probability distribution over all the actions. Each time the conversational component takes an action, it will receive an immediate reward from the user. If we ask an attribute, the user will say yes or no, and if we recommend some items, the user will accept or reject them. And it will guide the conversational component to learn the optimal policy. In this paper, there are 4 kinds of rewards. The first one is R success. It's a strongly positive reward when the recommendation is successful, and the second one is R ask. It's a positive reward when the user gives positive feedback to on the ask the attribute, and the third one is R quit. It's a strongly negative reward if the user quit the conversation, and the last one is R prevent. It's a slightly negative reward on each turn to discourage long conversations. And the total reward at each turn T is the sum of the 4 rewards. And to optimize the policy network, we can use the policy gradient method formulated as this equation. Here pi is the policy network, and theta is the parameter of the policy network. RT is the total reward accumulating from turn T to the final turn. And the last stage is refraction. If the system pushes the recommended items to the users, but it gets rejected, we need to update the model in the refraction stage for better recommendation in future. If the user rejects the recommended items, it means that we need to assign lower scores to these items. This can be done by updating the factorization machine model online. And we can define a BPR loss function like the offline training process. And here V is the interacted item, and V is the rejected items we recommended. And this update is done online. Next is the experiments. The data sets this paper uses is one is for business recommendation, and the other is for music artist recommendation. And the experiments in the paper covers the overall performance, the contribution of the attribute where BP are in the estimation stage, and the state vectors in the action stage, and the online update method in the reflection stage. But today, I will only cover the overall performance in this presentation. This table shows the performance of 4 different algorithms. Here, absolutely greedy recommends items in every turn without asking any questions. And once the recommended items is rejected, it updates the model. And the max entropy asks the attributes that has the maximum entropy among the candidate items in each turn, and it chooses to push the recommendations when the candidate space is small. And CRM is the state-of-the-art method, which is similar to ER. Here the matrix SR at T is the ratio of successful conversations that the method recommended round choose the ground choose items by the term T. And AT is the average number of turns that the method recommends successfully. We can see that there is a significant improvement of the EAR compared to the other methods. And these pictures shows the success rate of each method in different turns compared to CRM. We can see that absolutely greedy is better than the other methods at the beginning. But this is because the other methods like to ask questions at the beginning. As the conversation goes, the success rate of absolutely greedy will fall behind the other methods. And it shows that asking question is useful in the multi-round conversational recommendation scenario. And here EAR generally outperforms the state-of-the-art method CRM. The reason is that the conversational component of CRM doesn't utilize the information from the recommender component, and it demonstrates that the EAR is more efficient in a more complicated multi-round scenario. That's all of my presentation. Yeah, any questions?
Okay, let's thank Jiaqi for his presentation. So I invite you to ask some clarification questions. Yisong has also clarified a little bit on the paper because, of course, he's the primary author on it. So maybe it's more clear from Yisong's presentation also about what we mean by quitting, right?
Oh yeah. So every conversation session will comes to an end, right? So now we the only condition that user quits is in 2 ways. The first way is the recommendation is successful, and meaning that the system has pushed the item that the user likes. And the second way, and here used as a strong negative reward for the reinforcement learning module is another quitting condition is that the conversation goes beyond 15 turns. This is because we use a user simulator to study CRS, and the only reasonable way now we can think about is that the conversation goes beyond a certain tense, a certain amount of turns. There might be some other conditions like the recommendation hasn't been successful in like 3 or 5 turns continuously, but we haven't tried that because if we try that, we need to justify that. So now we only use a simple way for user to quit is to go beyond a certain amount of turns. Any more questions regarding Jiaqi's presentation?
I think, Jiaqi, you can also ask questions to Yisong because he, of course, knows this paper very well.
I already asked some questions before.
Okay.
Yeah, we chatted on Slack. Yeah.
Yeah. So I invite the rest of you, since it's not very often we have the author of the paper sitting here. You know, you can ask your really tough questions like, well, why did you bother writing this? It doesn't look very novel, or something like that. And, you can have a good grilling session. Yeah. So Yisong, well, you know, since you wrote this work, it's been very well received. I mean, you guys, Wenchang and you have both been very good at making sure people know about the work and utilize it. What do you think is the most important idea from your paper that the previous works don't consider? I mean, we've already reviewed the SIGIR 20 work, which actually came after. You know, at the same time as your work. So I'm wondering whether you can help seed some information or some opinion from you about what you've considered the most interesting aspect of the paper.
Yeah, sure. Recently, our system has been considered or tried by some industrial partners from Kuaishou, China, and Alibaba, China. And these guys have come to me to discuss with me. From their feedbacks, they think, and also I think, the most significant part of this paper is a clear problem formalization. This paper has a clear problem formalization as it has distilled the 3 key challenges in CRS. Just like Jiaqi has covered, the first challenge is that what to ask, what to recommend. The second challenge is when to ask, when to recommend. Finally, how to adapt to users' feedback. And these industrial partners really like this, this formalization, and they commented that we have dig a good hole. Dig a good hole is a Chinese idiom, meaning that we dig a good hole and other people can pour water into this hole. Yeah. So I think the most significant part is the problem formalization. Yeah.
Thanks, Yisong. So other people, would you like to comment on anything? I can always waste time and talk about related and not so related things about IJCAI and other papers. So I invite all of you, who especially our PhD students, you guys need to ask questions. You don't ask questions, you don't know which questions are worth asking. So please go ask a question if you're sitting here and you're listening. No questions. I'm embarrassed. Can I enlarge it to the rest of you? So our external guests, whether any of our external guests would like to ask a question?
Yeah, any question is welcome.
Okay, I'll start with one. Okay, so you talk about a single attribute to ask, when to recommend items, and how to adapt to online feedback. I'm wondering where you think the most work has been done lately. Is it on the adaptation or on you know, when to ask? I think it's clear that at the beginning of a conversation, it might be good to ask for information. But is it ever the case in which the system is so confident that it doesn't need to ask, it'll just recommend right away, even in a conversation? Like, I think we all know some pushy personalities in our friends or family who would just go ahead and recommend certain things without being asked your opinion, you know? So if we can think about like those pushy people in our families or friends that might just say, well, I think we should do this, or I think we should go eat that. Are there cases like that the recommendation system is actually very sure that it should recommend items?
Well, I think there is one baseline exactly corresponds to what you just said. The baseline is absolute greedy, right? So there's one baseline doing it. And I think proof mean just, I mean, refer to sort of like the persona or the personality of the system to be a pushy person, to be a pushy agent or a patient agent. Well, I think during, according to my case study, our year system appears to be a very patient agent. It's gradually ask a few questions, like 2 or 3, then later it became confident to make a recommendation. Yeah.
I think we'll see that in certain modalities or implementations, a pushy agent is more favorable than one that's not. You know, when you have very little attention and you're not able to formalize an answer to something, maybe being able to say yes, no to something is easier than producing an answer to, you know, a preference.
Attribute.
Yeah, an attribute. So if I'm driving and I want to recommend a restaurant recommendation, maybe I just want you to choose. Okay, I don't want to give so much information because I'm constrained, right? But other cases where the stakes would be higher, let's say I want to know who to date, right? Probably I don't want to take the first recommendation. I want you to, you know, take my preferences into account more before you recommend items, right? Like where, you know, I think you may have been in a situation where a pushy relative asked you, you know, when are you going to get married or whatever, and then they start recommending, you know, XYZ person to you who you don't have any clue about. So yeah, I'm just thinking, you know, those types of dynamics about the human environment, not the mathematical environment, the human environment of recommendation is important. And like I said earlier, while we are in the case where AI systems are more and more a part of what we do, it's possible that a recommendation agent runs into a user preference agent. Like, you know, let's say Cortana or Siri knows a lot about your own preferences, you know, modeled on, let's say, your smartphone device. So you have a smartphone device, right? It keeps preferences or history about you. How much of that gets revealed to a recommendation system? What type of protocol is that going to result in? The negotiation of that, and whether you as a human get to be involved in that. You know, I'm curious what you think of on those subjects.
Yeah, to be honest, I haven't thought about that before. I think they're very important questions. I mean, I think it's like how the information flows, right? How our inputs to the system can be later leveraged by the system. I think they're very good questions, and I haven't got an answer now.
Okay, yeah, these are just seeds. So again, if you guys would like to ask, so Shinza has his hand up. So thank you, Shinza, for asking.
Because I have probably a question. So I remember you said that for your quit, you simulate the user such that the quits fixed after 15 rounds of questions. So I have an idea. I'm not sure if it's a good idea, but I think because people are some people are more patient, some people are less patient. I mean, for me personally, of course, I probably will get very impatient after 15 rounds of questions, but I know there are people out there who might quit like when he see the first question. Like, so probably you can consider adding some type of random function to the to the patient's level of the people, and like there's a distribution. Like most people are impatient at around 15 questions. Some people are impatient at around 10 questions. Very few people are like impatient like when he meets the first question, like something like that.
So you're saying
I think
the patience of an individual or a topic, right?
Yeah.
So for certain things, I might be impatient. For other things, I might not be. And for certain people, they may have more patience than others.
Yeah, I think that there should be a distribution, and how you distribute it, probably you can do it according to some survey or.
So we can think of it as a latent variable to be estimated.
Yeah.
Actually, I remember there are some related work doing this kind of job. The work published by Baidu in this in ACL this year is kind of given the prediction of when to stop the conversation. Is to, I remember there's classifier to input to handle the input of the number of conversation, the range of conversation, and some others latent factors. So to determine when to stop the conversation. It's kind of the similar idea. If you're interested, you can look into that work.
And also to me, it also, I mean, the use case also matters. For example, if I'm just watching video on YouTube, I won't bother to answer like 10 questions to know what video I should watch next. But if I'm buying a very expensive stuff, then I would maybe want to spend more time to answer the questions.
Yes, I think it's a very good point, and I think the system can be improved by your idea, like in this way to categorize or to plan the conversation before it starts, given some inputs, like now the user wants a extensive option, then its planning can be a long conversation. However, if the user wants a cheap option or convenient option, then it's a short conversation. Yeah, I think it's a good point. However, I think it still lie in the problem of user simulation. So we use a simulated user to do the CRS research, and I think we really need to build a convincing simulator to address that. Yeah.
Okay, so I'm glad we all had a little bit of conversation. So thank you all for participating. So we'll come back to the reading group now, and Yisong can put in more information into the Slack. So
sure.
In the meantime, we will go ahead and go with the next explainable explainable lecture. So maybe we'll thank again for the presentation, and then we'll go on to the next presenter.
Okay, I guess it's me this time.
Okay, so Victor, you can share your screen when you're ready.
Okay. You see my screen?
Yes.
Okay, today I'm going to introduce dynamic online conversation recommendation. And this is a paper published in this year's IJCAI.
Okay.
And, my name is Hansheng. First, I would like to introduce its motivation. So in the social media, and there is many trending topics, and for persons, they also have dynamic interest. And for this paper, it claims that works in the current conversational recommendation systems always assume static user interest. And also, if we want to better handle cold start problem, that where the conversational or users are new and unseen in the training, that we need dynamic online conversational recommendation systems. And here, the right side is example the paper gave for a person's interest change. At the first, the conversation 1 and 2, the person is talking about something related to internet security. And then his interest changed in the about operating systems, and he started to talk Oracle and kernel and Ubuntu, something like this. And this is so-called interest change. And the proposed model try to and modeling and handle this. So the following I will talk about the approach. And the proposed model try to capture the user interest from the conversation he talked about in the past, and from the interaction that he engaged in the conversation with each other. The model try to capture the representation from users' chatting history, and he using a gate recurrent unit to model this. And the second, the model user are using a BGRU and a GCN to modeling the user's interaction in the conversation context. That is in the Reddit, they have conversation and many users join a conversation and they will have interaction because of the replying comments, something like this. And they also propose a user-aware attention to convey the user interest dynamics. And finally, they use the user's information and the conversational representation generated by the attention and GCN to predict how likely a user will engage in a conversation. That is a score, that's the probability a user is interested in a conversation. And here is the overall structure. Here is the input. M and U is one user. M is the historical message. And T, here is the input of conversation. T represents the turns. The model divided a conversation into many turns. And the output is this user, and with this conversation, and the predict score that this user would like to engage in this conversation. I hope the input and output is clear. And the left side will be the user model. And they use a message encoder to model this user's interest in the past. And the red side is conversational or level modeling. In this conversation, it has many turns, and it has many users, and it will modeling the conversation's representation via the relationship between these users and the information of in these terms. Then we will use the conversation representation, the user implementation to generate to use attention to get a final representation of this conversation, and between these two to generate a predict score. So I will talk about go through in detail from the left to right and to the top. The first is the message level model. Let's say it's given a user's historical message and use a pre-trained word embedding layer and CNN to encode this message to a representation. Then for a user, it will have many messages. For uses message representations, the model uses a GRU encoder to with a time order to get these users representations, and this is a left set in the overall structure. And then we go to the right set. The right set is a bit complex, and so the first it will encode the words in turn level. I mean, generate a representation for each turn. And that is very similar to message level modeling. That's using a pre-trained word embedding layer and CNN to get this turn level representation. Then the model try to encode the interaction between conversation turns with so-called conversational level modeling, and that is used by BGRU and GCN. I will talk about in detail this later. And finally, it will use a user's representation generated by the left set of the overall structure and apply attention onto the output of the third component, third step. For this conversational modeling, and the first is we will use the chronological order. That is, employ a B GRU, which actually 2 GRU. That is, in a turn, we will have many messages, and it will ordered by time, and we can apply a GRU on it from that in 2 directions, and finally concave the forward and the backward hidden states as the representation for this term. Okay, then after we get this representation for each term, because in a conversation, such as Reddit, they will have a relationship between each term, and maybe some is common and some is reply, whatever. And this model defines 3 types of interaction. That is predecessor to the successor, and self interactions, and predecessor interactions. They use GCN to model it, which is actually, we can view it as 3 GCN, I think. And they have 3 types of edge. The first is self interaction, and these 3 types of edge. And we have 3 graphs. One graph has 1 type of edge, and we apply GCN on it. And the node is each turn's representation. And after this GCN, we have generate conversational level representations. And after we get these representations, the model apply user-aware attention on it. That is, in the user level modeling, we got a user representation from its historical messages by a GRU. And now we got this representation with representation in each turn, what you say, in each node. And for in the graph, each node we have this a new representation, and we apply a softmax to it. So we get a weight for each node, what you say, each for each turn. Then just sum it by the weight, and we get a whole representation for the conversation. So, and finally, basically it's a 3 linear layer, and we input the user's representation and the whole conversation representation, and basically we use 3 linear layer and get a score for this. Finally, following with sigmoid, and get a score for the probability. And the learning objective it uses a weighted binary cross entropy loss because when it's going to train it for conversation, there are only several users we are engaging, but it has a large user list. So I believe that their positive samples will be far more less than its negative sample. And so they use the weighted binary cross entropy loss. And then come to the experiment. The data set is produced by their own. They collect data posted from January to May 2015 on 3 subreddits on the discussion topic technology, today I learned, and funny. And they removed the conversation with only one term and produced 3 data sets of different topics corresponding to these 3 tech, learn, and find. And here is the statics of the data set. Here I think there's a few points I need to explain. His HIS number, this is the average history number a user had. And new user rate means because the training data is data from January to April, and the validation data and the test data is May. Posted data posted in the May. So the new user rate corresponding to that, the user only appear in the May, not before, and this is new user rate. New conversation rate means that because a post may be continuous from, for example, February to May, and that is old conversation. New conversation rate means that this conversation begin in the May and never seen in the train. Okay, and the red set is, the distribution of the conversations graph graph construction. The path means because a conversation in the Reddit may have several branches, then the path is means that from the beginning of the post to leave discussion, and here means many graphs or say conversation only have one path, and some have 2 or more. That is, and this is the main experiment of the its paper. They choose some simple baselines, and as a state-of-the-art CRNN for unchanged interest. They also change some dynamic interest model such as RNN and RCRNN. From the table that we can say that this model is obviously outperformed from the others, and they use the 3 evaluation methods with MLAP and the precision 1 in SIGIR. Okay. They also did some more experiments. The first is conversational co-star. In the data statics, I introduced above that there is some users which only appear in the May. So they separate the test set into future conversation and existing ones, and then compute the result on these 2 separate data sets. And the following is the result. They only compare the state of the art in the unchanged interest model and the LCR. From the table, we can see this model is significantly better. They also did ablation study. The first, from the result, we can say that each module can contribute significantly to the full model, and user factor embedding that contribute most. And the BGRU and Jiahao also has significant impact. No, that's all. Thank you, and any question?
Okay, any questions for Hansheng presenting the dynamic paper? So I know we're a little bit behind. We still have Victor's presentation on explainable recommendation, but I'd like to invite somebody to try to summarize what was discussed. So if we have any of the scribes for this week who are giving updates for it, maybe we can get some idea about what the paper was about. So I've seen one person scribing most of the time, but I'm wondering whether there are others helping out today. So Hansheng, maybe I can ask you then, what do you think is the core innovation that improves against the previous state of the art, which is also from their group, right? So they had this CRIM model, right? Interest model, and now they're moving into a dynamic one. Where do you think it helps the most?
I think the improvement maybe mainly came from the modeling the users' interactions in this conversation.
So when does a user change their mind or change ideas that was such that a dynamic system would be particularly helpful?
I think that in this work, that the main part will be that in a conversation, then it divides. I mean the relationship between each term. I think that may be the crucial part of the full model, and I mean, when the left side of the module modeling the historical interest of this user, and when this user engaging out in the conversation, that I believe that one may be learn something with the interaction of in this conversation. For example, if this interaction is very, I mean, not sparse, and for this topic, and then we can say that maybe the user is being more interested in this, something like that. That's what I understand.
Okay. Yeah, I think we can all think about our own conversations that we have on social media and when a dynamic system would make sense there. So this is quite different from the other works that we've seen earlier today, which are, more e-commerce directed type of recommendation. But when we're talking about more of a conversational nature, we have very different things. I mean, you can think about your own discussion forums or your own email where things change, right? You can add new participants into a conversation and it changes the nature of the conversation. So there's a dynamic interest there, or you might just change the subject without even remembering to change the subject line, right? So within the same conversation, you actually start to talk about something different. So having a topic detection or a dynamic shift is important for those types of things. Okay, so let's thank Hansheng again for the presentation. And we have our, I think, last presenter, is that right? Hengchang, are you presenting today? I wasn't sure. Okay, but in any case, I think now Victor is going to present the explainable work. Yeah.
Okay. So can you see my screen?
Yep.
Okay, so you still take around like 20 minutes for my presentation.
Yeah, so if anyone needs to go, you can go ahead. I mean, the recording is going to be on YouTube, so if you want to watch it later, that's fine as well.
Okay, so I'll start with my presentation towards explainable conversational recommendation. I will go as the same step in the paper. We go through introduction and then we formulate the problem. I will describe the model and finally I'll show you the results and discussion. So firstly, for the explanation in a recommendation system. The recommendation system which predicts the user's personalized preference have become one of the most effective methods for the overcoming information overload. And recently, researchers have shown that both the accuracy and explainability are essential for a recommendation system. It has been shown that explainability can not only improve the user satisfaction, but also improve their trust on the recommendation system, as well as improve the efficiency of a certain recommendation system. The effect is not only one directional. It can also help the users to understand the working mechanism of the recommendation system and also trigger some potential feedback between the users and the recommendations. For us who are going to tune the recommendation system, right, it also helps us to understand why the recommendation system is making the wrong recommendation. For example, if we are trying to recommend a movie to a certain user, and then we give the explanation that it is you will like it because it's a documentary movie. And finally, the user will realize that he doesn't like this kind of movie at all. So we are making a wrong recommendation. And also we can, by doing the explanation and conversation, we can understand some immediate updates from the users. For example, if he's action movie fans, but suddenly want to change his idea to watch some documentary movie, so we can quickly adjust that and make a recommendation accordingly. And the third one is that by doing this, we encourage the interaction between the users and the recommendation and our recommendation machine, so that we can also collect more data for the future purpose. So for this paper, what I will focus on is to integrate users' feedback into explainable recommendation system, and to enable the bidirectional user and model communications. Meanwhile, we also provide an alternation interaction paradigm. Instead of asking what would you like to have in the recommendation, we give recommendation and explanation and ask whether you accept this recommendation. And the final objective is fulfill these three goals in accuracy, explainability, and also satisfy the user's requirement from their feedbacks. So here we show a simple example of how we are doing this recommendation, how we are doing this conversational recommendation. So first, the model will give out the recommendation and explain why he's doing that. And the users will give out his feedback accordingly. And then we'll go for a few rounds. And finally, right, the model will give out something that users enjoy. So it can also be like, it can also be seen from this pipeline. Okay, so we could observe that, right, we first collect the user ID and some site information from the user's review and the reviews of certain items. And then we feed all those information into our ECR system. And finally, we recommend, we give the recommend to the users based on the recommendation scores. And we also give some explanations to the users. And then we collect the feedback from the users. As you can see here, the feedback part contains three components. One is the positive feedback. Another one is the negative feedback, as well as negative items that the users doesn't like. Why we are having the negative items is because it's kind of a trigger to tell the system when to stop. The negative feedback is the last recommendation we have made to the user. If it's negative, then we should go on with the system. If it's If it's positive, means the user liked it, then we should stop the recommendation. Okay, so here I will briefly describe the models. After we collect the user and item set information, right, we feed them into a context-aware concept embedding, and then we output the concepts embeddings of the reviews from the user and the reviews made to a certain item. Then all those concepts are feed into another co-attentive concept importance modeling layer, and this model will help us to see the covariance between the users and items concept, and output the probability that's importance in the user item pairs. We'll do the same thing for the concepts from the feedbacks, and then those two concepts will go through the multi-view concept selection and output the selected concepts. So for this part, we will doing the output of both the recommendation scores and their explanation. The recommendation score will be used to decide which of the items should be recommended. The explanation will be feed into another network to generate the recommendation sentence. Explanation sentence, sorry. And so in the next few slides, I will go in detail about each model, and we see how it works. So firstly, for this context-aware concept embedding, right, we will take the concept, we will take both the word embedding and the context embedding. So the word embedding is calculated using the word embedding lookup layer, and the concept embedding is calculated using the by averaging the embeddings of related reviews. And for the co-attentive concept importance modeling, we'll do 3 different steps. The first step is to calculate the co-attention weight matrix phi from the user and item interactions. Here, the WC and the I functions are learnable. The WC is a learning weight matrix, and the I function is a feed-forward neural network. For the second step, we will calculate the concept importance vector. This one is done by using the softmax function to calculate the by using the softmax function on the co-attentive weighting matrix. And then we will find out the AI and BJ, which represents the probability that a concept in the review is important for the user item pairs. So those concepts with a larger probability will be easily selected into the explanation. And finally, we will calculate the concept level feedback loss. The loss will calculate by this function, and the AI and AJ here stands for those positive concept or negative concepts that appears in the that corresponds to the user's feedback, and it denotes that the probability of the concept is considered important. So after this, we'll do the same stuff, the local propagation of user concept interest for the reviews from the feedback.
Sorry, I do not catch where you, in the previous slide, where the feedback used in this co-attentive concept importance modeling. How it can incorporate this?
I mean, like which step? We have 3 steps here, right?
Yeah, but in the chart, it seems like the feedback also incorporates some information into.
Oh yeah. I mean, feedback is from here, right? Because here we calculate AI and BJ, right? And
yeah.
in this lecture we have the AI plus and AJ plus. The AI plus means like those AI correspond to the some concept from the feedback. So it's not the same AI here. It only select few AIs that correspond to the feedback. So
okay, I see.
Yeah. So that's why we have combined feedback here.
Okay, so the feedback is kind of filtering.
Yeah, I don't understand what's the filtering. I kind of, but we only want to know like what kind of the concept is related to the feedback, because the feedback is given by the user. If the user say he likes that, then you know that for certain he will like this kind of recommendation. So you're kind of giving that priority on the feedback part. So in all those, I will give quite a lot loss function later. If you see there's an act here, that means that the loss function is related to the feedback. Okay, so for this one, we are doing almost the same thing for the feedbacks, the concepts from the feedbacks. And first, we are doing aggregated embedding, which will embed the concepts from feedbacks, combining the previous the embedding from previous run and the current run. The FT here is also a learn more parameter. And then we'll calculate the preference score beta. The beta is calculated by this function, and it's between the embedding and aggregating the embeddings. And because of this triangle inequality, so the beta will always vary from -1 to 1, which represents the unsatisfaction, the range from unsatisfaction to satisfaction. So finally, we also use the softmax function to choose those important vectors, AI star and BJ stars. So that's the okay. So that's the part for incremental cross knowledge explanation, and then we'll introduce the incremental multitask prediction. So for this part, it mainly do two stuff. One is to calculate the user and item embeddings and recommendation scores, and another one is to determine the keywords that must appear in the explanation. So we'll go in the multi-view first. So for the multi-view, it refers to the global view and local view. The global view means we learn the recommendation system based on all the training samples. And the local view ensures that we learn from the user's feedback. We learn from whether the user is satisfied or not from his feedbacks and considering the local user item interest. Okay, so for the group one, we use factorization machine based model to come out with the recommendation score. And we will learn the loss function first from the offline training instance. The offline here means without any feedback. And then this RUV means the user likes the items, and this RUV pairs means the user doesn't like the items. So we calculate this loss function. And then we will train the whole model based on the feedbacks. So it's another similar loss function. Okay. So after that, we'll do the local estimation of the user item interest. The local estimation is done by the calculating a satisfaction score. This score is calculated based on whether the user is satisfied with the recommendation. If it's satisfied, here the score is this part. If he is satisfied, then you have a score of 1. If it doesn't satisfy, then have a score of 0. So it's a binary variable. And then we also doing the aggregating things to combine the current one with the score in previous one. And we also like it to learn the parameter alpha t. And finally, we combine the multi-view, which is the local view and global view. We also feed the result from global view and local view into the system. We also like the system to decide the parameter alpha r. Okay, and then it is also the loss function is also similar to the previous view. Okay. So and for another part is to generate the explanation. So for this part, we have first we settle down two constraints. The constraint one is to select the concept CV that must appear in the explanation. And constraint 2 is to punish the model if other selected concepts are not included. So for constraint 1, we solve this problem by using, by first locate the most important concept CV, and then we use two GRU model. One is forward and another one is backward. So we will output the important concept first, and then we will use one GRU model to generate from the concept to the beginning of the sentence. Then we use another one going forward to generate the words from the context until the end of the sentence. So it was solved by 2 GRUs. And for constraint 2, we will solve that by calculate the concept relevance loss. Right, and here in the loss term, you can see that the SK stands for the, if SK is 1, that means that the case word is a concept that has been selected for the user item pair. If it's 0, then means the certain concept is not selected. And the O here stands for the probability of a word being generated. So we also do the minimization of this loss function.
So the input here is sentence or concept?
I think it is the input here is the concept, and we try to generate the sentence. And we also punish those sentence because we see that if the sentence contains other important concepts.
Oh, so the explanation here is a kind of sentence. I misunderstand it. I suppose it's be a concept.
Yes, it's a concept, but finally, what we do is to output something like, I think like this way, because I think in this sentence, let's take the first example, right? This is a dark comedy with great cast. I think in this sentence, the concept must be a dark comedy or the comedy, and then we will generate the whole sentence accordingly. Maybe the most important one is the comedy, and then another important concept is the dark.
Oh, okay, I see. Okay, so the explanation is to explain the concept. Oh, I suppose it's the model explanation.
Oh, okay. So
it's the item recommendation, right? Not the model. Yeah.
So I will continue for this one. So finally, we will train the whole model based on these 2 loss function. Yeah. So all the items I have shown before, right? The loss function, and the only item that I didn't say before is the phi here, right? So the phi here represents the model parameters, and if we have a star here, that means it represents the model parameter in previous one. So we are trying to minimize those 2 loss functions. Okay, it comes to the experiment part. Okay, the experiment part is easier compared with the model part. So for this part, we adopt the 2 public available dataset. One is the Amazon dataset. We select the electronics and movies part. Another one is the Yelp dataset, which contains the review of the restaurant. And we adopt our baseline model is the NRT and CML, and then we compare our different objectives with them. We will examine the accuracy by using the HR, NDGG, and MRR method. And we also do the explanation quality evaluation by the BLEU and Hengchang model. Those are the widely adopted measures to measure the similarity between ground truth and generated text. So we'll see the result from here. So first, from this huge graph, you can see that our model outperforms all the other models in all the objectives. And here, our G means that we train our model only through a global view. Okay, and in this graph, you plot the accuracy and explainability compared with other models with respect to the number of conversation terms. So it could be seen that if you have more conversation, then you can have a more accurate recommendation and also have a more explainability score. We will limit the training terms to 5 terms in this experiment. And for this graph, it shows that when we ask the human beings to evaluate the models, to evaluate the fluency and usefulness of the explanation, you can also see that our model outperforms with other 2 baseline models. And another very important findings can be seen from this table. So if we have a look at the previous 5 evaluation, to see that our model performs our model trained with only the global view or only with the local view. It also outperforms the model only trained with positive feedbacks or only trained with negative feedbacks. So it gives us very good hint about the effectiveness of multi-view learning. So here the CSR score is, it means the concept level feedback satisfaction ratio. So we'll consider a concept to be satisfied if it appears in the explanation. And if I will consider the negative concept to be satisfied if the concept is removed from the explanation. As I explained to you, right, because the local view only focus on the feedback from users, so you can achieve the CSR score of 1. So that's the also it shows the effect of different users simulation settings. So finally, we can conclude this paper in these 3 main contributions. So first is design an incremental multi-task learning framework. And then it proposed a multi-view feedback integration method. And finally, evaluate the proposed method with different settings of similarity users and human assessors. And that's the end for my presentation. Thank you for listening.
Okay, right on time. You said it would take up to 20 minutes. It did take 20 minutes, even with questions. So congratulations, you're right on time. Yeah. So, you know, I know many of you may need to leave, and that's okay. But I encourage you again to try to participate a little bit. So any questions? I think one of the interesting thing about justifications is that you know, we are still thinking about justifications of individual items, okay? But many times when we make a recommendation, we have to deal with the last piece of information as well, right? So let's say I don't want French food, I want Chinese food or something like that, you know, then it actually is helpful for a recommendation system to specifically state something like, you know, here is a Chinese restaurant, not a French one, you know, something like that. So to be able to helpfully coordinate with the user, be empathetic and say, you know, I heard and understand what you said. You know, this is definitely not a French restaurant. Or, you know, this is definitely not an expensive item, or this is definitely a quality item, you know, compared to the one that I suggested earlier. But right now we haven't come to the state where we have a really good idea of how to do this type of comparison against a cohort of objects. So I think that's an interesting place to go forward. The other thing that I think from today's lecture is that we see that there is a thread that Yisong mentioned earlier that is very important, that all of these papers sort of deal with, but not directly, and that's simulation, right? The simulation of turns in order to do the reinforcement and the guiding of these policies about how to, when to decide to do explanation, maybe something that doesn't always need to be there, okay? And when to decide to ask. All of these things are policy decisions that that need to be rolled out in a decision framework, right? If you're talking about a MDP or POMDP or something like that. So those are I think, very interesting areas that you can all think about, you know, in conversation recommendation. Like, how do we get silver and bronze data, you know, to do this distance supervision, to do to make as Yisong said, one of the big challenges is how do you get a plausible simulator, right? And what method can we do that? Can we train an adversarial method to come up with a simulator that could be based on GPT or T5 or whatever, or, you know, not even in English, you know, in Chinese or another language, and within the domain that makes sense. So with that, I think things will be much more interesting in the next couple of years. So again, like I wrote on the general channel, our next 6101 next semester is likely to just build on and maybe recap, these two lectures that we have on conversational recommendation systems. Okay. Secondly, I think all of you have heard, especially those of you who are doing projects that I have tried over the last 2 hours or so, to give some high-level comments to your projects. So I've been multitasking a little bit to give you that. So if you have any questions about the feedback or you want more, you can certainly engage me. And if possible, do it on the project channel, because I think it's very helpful for everyone else to look at your abstracts and then look at the comments that each other you can make to each other. So if you know something about an area that the other people may or may not, please do share. Because more often than not, even though you know something and you're pretty sure the other person knows, it actually happens most of the time that they don't know, okay? Because there's just too many things going on. So it's important to share information. That's the whole point of having a research group rather than research individuals, okay? Finally, STEPS, which is happening in week 13. I've gotten an update from the organizers. They're going to send out more details later, but basically there are two clarifications that have been made. Okay, one is that it's actually going to be a virtual event, so that means anyone in any time zone can attend. Okay, it is open to the general public. A registration will be needed at some point, but you guys, as virtual being presenters, are already registered. Okay, it will be done by Zoom. So Zoom has a recent feature that allows breakout rooms to be something that you can choose. It used to be something that you could only go into the breakout room assigned by the host, but now I think you're allowed to go to any breakout room that you signpost that you want to go to. So I think with that, it will be easier to manage some type of hosting event where there are multiple breakout sessions, okay? So that will be the technology platform for enabling a virtual project showcase. Finally, and this is more of a problem or a feature, depending on what you think, the session will be held from 3 o'clock to 8 o'clock. So 15 o'clock to 20 o'clock in 24-hour time on Wednesday, on week 13, so that'll be November 11th, okay? If you cannot make it for that time because you're in a business meeting or you have another class or other things, we totally understand. Do let us know. What we would try to do is make arrangements so that somebody can help cover that presentation for you, especially if you're in a small group. This may be more of a problem. Okay, so do alert us to that early on if you have any difficulty there. Otherwise, it's great if you can be around for certain part of the showcase in case people want to come to your presentation. You don't have to stay obviously for the whole 5 hours, but it would be nice if we could arrange a couple 30-minute slots, maybe 2 of them, in which you're present to take and answer questions, because otherwise being in a breakout room for 5 hours is almost like jail time. I don't think it's very healthy for anyone. So I appreciate you're working with us and trying to figure out what the right way to go about dealing with STEPS. If you have suggestions and you've participated in a virtual conference or event and you found it worked really well, then let me know, and then we will try to see how we can permute the rules for 6101 within the larger STEPS event to happen successfully. Okay, and with that, we are done. It's been 2.5 hours, so thank you very much for staying all the way through, and we'll see you next week for the second half of the conversational recommendation systems. Now, yeah, I think that's all we have, right, Shinza? Thanks very much for clapping virtually. So let's give a big hand for all of our